So we have what ends up being a pretty standard situation for these type of problems is we're going to have a nice schematic like this where we're loading in shear. Now, we talked about loading in tension, loading in shear. Hopefully you guys picked up on most of what we talk about here when we're talking about fillet welds ends up being shear loading. So if we're loading this way and we're welding around here, that's a shear load. At the very end today, we talked about the formulas for tension and the formulas for shear. There was no difference between the two of them, right? You have a load, you divide it by an area, ended up being exactly the same. We're still using the throat area. There's some amount of kind of conservatism in there because you probably know that if you load something in shear and you load something in tension, you might not fail along exactly the same path. We're not worrying about any of that, but just so you guys are aware, when you're looking at something like this, hopefully you're thinking of it. This is in 2D. This is a plate here in front and a plate on the back. They're sliding relative to each other. So I'm spending a little bit longer on this because it's really important if you guys have the right visualization of what we're looking at. It's going to make everything easier. Does everyone get that? Everyone knows what we're looking at when we look at these two plates? So we're given some dimensions here. This is 200 millimeters. And this length is also 200 millimeters. And we're given a load of 675 kilonewtons. And we're told this is 300 W steel, 12 millimeters thick. So the first part of this we're not going to worry about doing up here. If you guys have the example, you'll see the first part. This was from a previous exam. And the question was, what are the minimum and maximum leg sizes according to the Canadian Institute of Steel Construction? Hopefully you know the only thing from this you need to solve that is you know the thickness of your plate. You can go into those requirements, figure out that for a 12 millimeter plate, your minimum thickness is going to be, let's see here, just to make sure. Your minimum thickness is going to tell you you should have at least a 5 millimeter leg size, and the maximum is going to be, anyone remember? This is more than 6 millimeters. T minus 2, I heard that somewhere. The maximum is going to be 10 millimeters, right, for a 12 millimeter. So we were not, that's, hopefully if you guys go through the notes and remember that those are going to be, I believe those rules are provided, like the CISC guidelines are always going to be provided in the formula sheet. So it's just knowing you have to pull that 12 millimeters, go to those guidelines, pick the right number off the chart. Hopefully that's going to be the easiest part of this exam is if you get asked what are the minimum maximum allowable per the guidelines. The harder part is going to be what we're going to ask you to do here, which is, let's see here, say calculate, come here. So there's a few extra conditions that are put in the example, but two things I want to draw your attention to. One, first I'll show you where the fillet is here. So we're considering a fillet that goes along this whole length here. Now, we've said assuming it's constant. I think that's said in most of the examples. I don't think there's actually been any examples on previous exams where we deal with fillets that are a different size. So if this fillet is a little bit thicker than this fillet or this fillet, why do you guys think that is? That's exactly right. It's because this is the simplest situation. Now that doesn't mean it's the best situation, doesn't mean it's the only situation you come across. Hopefully you guys as you go through the simple situations, you see we've given you all the tools to handle the most complicated situations. So we're not showing you here what is a rule of thumb that says always your fillet weld should all be the same size. Something I was talking to Dr. Mendez about at the very end of class is part of the reason I think that this is probably going to be, I think from this point in the class onward, gets to be a little bit harder to grasp the concepts, is because we've moved from kind of simple facts, rules to memorize at the very beginning of class, to more simple formulas where you plug and chug and there's the right answer, to design. And this is just kind of getting to the tip of design. But when you start to talk about design, it's not that there's not a right answer. Typically there is a best way to design something, but it's not always clear exactly how to get there. So rather than following a very strict formula to get an answer, you have to follow a procedure. And following that procedure is sometimes a little bit more difficult than if you just grab a formula, throw in numbers. Hopefully, once we go through these examples, you guys are going to get a feel for what that procedure is like. And if you do it step 1, step 2, step 3, like we've done in the other seminars, it's not that bad, and you do realize that you've got a lot of power in these equations, but it can be a little bit more complicated than if you're just pulling a single equation, plugging a value in. So as we go through this example, if anyone has any questions, please ask, because I want to make sure you guys all understand this. This is 100% what you should expect on the exam, is a question where you're given a diagram, either asked to solve for a load or asked to solve for a leg size. The welds could be at angles, there could be multiple welds. All of that is stuff that's covered in the notes. But this is your best chance to ask any questions about the procedure, so you guys are all 100% on board with what you need to do. So, what do you guys think our first step should be? Any thoughts? Okay, well, I'm going to give you guys the first step. It's very quiet in here. Is it week back after reading week? Everyone's still kind of asleep? I'm going to write out the equation. So, we had and this will be given in your formula sheet, but it's also from the notes in today's class. So we have look familiar to everyone? Yes? We saw this equation today. This is how this equation is going to be the key to all of what we're doing here. One thing I think that was mentioned fairly well in class, but just so we're clear, does anyone know what units this has? Right. So newtons per meter, or force, it could be pounds per inch, it could be kilogram force per centimeter, it could be any force per length. Typically we're going to do newtons per millimeter, newtons per meter. There are some examples, I think, which have imperial units. But it's the exact same math no matter what. Does anyone remember what units our AW has? Meters or millimeters? Right, so this is one of the interesting things with the way we've done this here. AW, this ends up being our throat, right? So it's not area, it's not millimeters squared. That's one thing that sometimes catches people, because you're looking, if you're not remembering, you didn't have it fresh from class, you're looking and you're thinking this is supposed to be an area, and you start adding things in where you're not expecting them, and you suddenly have all your dimensions not matching. So this is throat, so this is just length. So we looked at solving, I think, this is the same example we went through kind of very quickly in class, but if we have our welds, and we'll call this weld 1, weld 2, weld 3, what we're going to actually solve for is if we take this to the other side, we end up with VR over AW, and we're going to calculate our VR over AW for each of those welds. So if we start with weld 1, and we're going to make a little table here. Actually, let's see if I lost. I'm going to do it over here so we get lots of space. So when we're calculating this VR over AW, we have, I'm going to say, 4 things to worry about. We've got, well, this is, hopefully you guys know this is going to be the same for all of them. We have our phi W, XU, this term, and this term. Seem good? So we'll make a little table here with 4 columns. The first 2 are going to be pretty easy. It's the last 2 where we're going to have to do a little bit of math. So if we label here, this is phi W, XU, so anyone for welds, well, it's actually welds 1, 2, and 3. What values are we going to use for these first 2 columns? Right. So 0.67, you said 490, and you, where did you get that from? Right, yeah, so actually it's a little, I think it's...
Not here, like when the professor had the slides on.
Right, so we were given here that we have our material is 300W, so if you go back to those table for 300W, that has a ultimate tensile strength of about 440, and so what's considered a matching filler material is 490 or 70 KSI, so 70, 18, something like that would be what you'd use here. So for this, got 490. We're halfway done. We got 2 of our 4 columns. So this is the hard part. Does that, well, I would say harder part. Really, this whole process, if you follow it step by step, you do a table like this, you look at your welds as pieces. Hopefully, this is a procedure that once you do it a few times and you get a little bit of practice with some of the other examples, this is something that's not going to be the part of the exam that you're worried about. This is the part where you get that question, you open it up, you know exactly what to do, you run through it, and you move on. So for this, we have weld 1. So let's kind of off to the side here. Let's look at what our theta is for weld 1. 0? I like that. What about weld 2? And weld 3? So this is kind of going to be the easiest case of this calculation of this term here. Shouldn't even need a calculator. So this is 1, 1.5, 1. What about MW? Does anyone remember what this will be in the formula sheet, but does anyone remember what this phi 1 and phi 2 are? And actually, let me double check here. I think it's phi. Does anyone have the, is it theta? Okay. That makes more sense. Well, those are not great thetas, but so if we have theta 1 here, this is really just the theta we're worrying about for our current weld, right? Theta 2, does anyone remember what that is? Sorry?
The closest
Right, so in this case, closest to 90 is 90. Now, if you guys go through and do this, what you're going to realize is if you plug in, well, hopefully if you realize you plug in 90 and 90, it's going to be 1. So that one's easy. Now, if we plug in 0 and 90, the way this equation's been built is deliberately so that you have a number somewhere between 0.85 and 1. So 90 over 600 is 0.15, which means this is going to be 1. 0 over 600, obviously 0. 0.85 over 1 is 0.85. Does everyone see that? So, a few of you hopefully have calculators. If not, now's a good time to grab them. And we've got all the numbers we now need, so we're going to calculate this VR over AW for each of our welds. So whenever you get a number, just shout it out and I'll write it down. Anyone else get that? So we should have 0.67 times 0.67 times XU, which is 490. 187? I got 187 as well. Does everyone get 187?
Yeah.
Yeah? And that's for welds 1 and 3, we said, right? What about for weld 2? I heard 321, 330. 330? 330? Sounds like we got a bit of a consensus. So this column, so we're adding some other info. This is just information we were given. This is obviously information we're calculating. You could have this all as one big table. All of our welds are nice and simple. They're all the same length. So if we have all of our welds at 200 millimeters, we have VR over AW. Hopefully it's pretty easy to see that this VR over AW over L is just going to be this number times 200 millimeters. Now, we're going to stop for a second. Does everyone understand why we would want to calculate VR over AW over L? Or VR, sorry, over AW times L. So we said our VR over AW is a force per length. So if we have a force per length, we need to somehow compare this to a force that we've been given, right? So if we multiply this as and this is actually not, I think I'm getting, this is actually a force per length, sorry. So we have a force per length. That's probably not the right way to write that. But you guys know what I'm talking about, right? Here, I'll fix that. What it really is the force per area. And if we multiply our force per area times length, we get a force per length. But this length, this is the throat. So this is a force per area, where area is our throat, times length of weld. So, does this make things clearer or more complicated? Have I lost you guys now? Let's think about another way. So we have a force here. We have a 600, actually I think we're supposed to, well, I'll be consistent with what we're using. We used V. 675,000 newtons. We want our weld to be able to handle this force. We know that based on the properties of our weld, we have a certain capacity per unit length of weld, per unit length of throat. We have to compare that to this number. We have to somehow get those two numbers in the same units. So what I'm going to suggest we do is we leave this force alone and start to look at how we could adjust this. But really, maybe a better way of doing is saying, if we have some capacity required, V, that has to be less than or equal to our VR over AW times our throat, which someone's going to have to help me here. What do we use for our throat? I think it's, we'll use AW here, times L. Does that make sense? So we have a force that we're applying. In this case, we're saying that force has to be less than our capacity of our weld. Now, you could write this as equal to, but because we know we're going to round up, that wouldn't quite be right, so we're going to say less than or equal to. This you don't have to write down when you're doing this problem. This is just to make sure everyone's understanding why we're doing what we're doing. Does this make things a little bit clearer? So what we want to calculate is what this value needs to be so that this is true. So really, what we're going to see is our AW has to be greater than or equal to V times 1 over L times 1 over this VR over AW. Or V times this VR over AW times L. So we're calculating this because we're going to then plug it in to this formula. So that's a long way of explaining why we want to calculate this number, but hopefully that helps some of you. Is you guys all understanding a little bit why we're doing this procedure, how we're putting into a table here? Is this too slow, or are you guys all keeping up, falling asleep? Okay, so does anyone have these numbers for me now? If we do VR AW times that 200, yeah, 200 is in millimeters.
So do I have to convert it into meters?
Good question. When you do a table like this, what we really should do is we should keep track of our units. So our VR over AW is going to have its units determined by what we plugged in here. So of these terms we plugged in, only one of them have units. That's XU. XU was in MPa equals newtons per millimeter squared. So if you plug in L in millimeters, that's going to mean we have over here newtons per millimeter, which I'm going to suggest is a nice convenient unit to work with. If you plugged it in meters, you would have Newton meters per millimeter squared, which is probably going to cause you more trouble later. So if you wanted to deal with meters, I would suggest you then make sure you convert this to newtons per meter squared or pascals. If you're okay dealing with millimeters, just make sure you keep track of what your units are. That's a really good point though. So if we stick with our newtons per millimeter, what would we have here for numbers? I'm going to suggest it should be a little bit more than that because we have 187 times 200. So this is VR over AW times L, right? You were doing VR over AW divided by L, right? Yeah. Everyone else get that as well? All three of you calculating with me? 66,000? Give or take a few. I think if you look at the exam from the previous years, I think it was 65,988. We're not going to worry about those 12. So, one thing we didn't necessarily show here, but we could have, is actually this capacity. We should write this as a sum, because this is for all of your welds together, right? So really what we're going to do now is add a third column under here, where we're just going to worry about this. But what is our total capacity for all of our welds together? So if you guys add those together, what do we get for our total capacity? 140. Okay. So we're almost there. We got one step left. Can anyone help me out with it? What should we do with this number? So if we want to get AW and we have VR, we're going to take our sum of VR over AW, right? If we take V divided by V, sum of VR over AW, we're going to end up with our units of length. That's going to give us our weld size. So if we sub in, we've got 675,000 newtons over 140, 784 newtons per millimeter. What do we get for our required weld size? 4.7? Now, actually I misspoke there for a second. Is this our weld size? No, that's our weld throat, right? So if we have AW equals 4.7 millimeters, then I want to make sure I keep consistent with our notation here. You guys can correct me on what symbol we used for the lag in the notes, but we're just going to call it lag. The lag is going to equal what?
0.7
Right. And what do we get there?
6.7.
So, right, we're not going to make a 6.7 millimeter weld. We're going to make, well, we'll see. An 8 millimeter fillet weld. Now, one thing, if we were to go back and check, we talked a little bit about what our minimum maximum sizes were per CISC. Our min was 5 millimeters, our max was T-2, 10 millimeters. This is between those two, so we don't have to do anything further. If this was greater than our maximum, we have an issue because we can't make a weld that's big enough to handle the load, so we got to redesign the structure. If it's less than our minimum, we don't have an issue, we just round up to our minimum size. Does that make sense to everyone? One other thing we didn't do here, but in practice, you would probably want to do if you were designing this, and I think we talked about last class how you do that. We didn't check to make sure that we're not going to fail through the section. Now, we're designing the welds. We're going to focus on the formula for designing the welds, but this is part of a structure. We're kind of taking it for granted that if we have a 12 millimeter plate, we've been given the dimension here, we're assuming it's not going to fail when we put 675 kilonewtons on it. We're assuming whoever gave us this problem designed this structure so that our weld was what we had to worry about. This wasn't going to fail. But I think the formulas from last class, does anyone remember what I'm talking about? There's a formula to check to make sure that we're not going to fail in our base material. It's interesting because that's not really a welding problem at that point. That's just a design problem. Those formulas are something we could have done probably after I think all of you guys have taken Civi 270 or something equivalent. That's a really easy computation. That's an area, that's a force, you get a stress, you compare that to the failure stress of your material, and you know whether or not you're going to be fine. The only thing we've done a little bit differently in this class is we actually then looked at what the design code is going to tell us is the failure stress of our material. So, unfortunately, this is probably as simple as all of the exam examples are going to get. All we had was nice square welds, didn't have any complex loading, didn't have to calculate any crazy numbers for our theta. This is the base case. All the other examples you see are probably going to be at least this level of complexity when you first look at them, but it's the same procedure. If you do a table like this, if you calculate your values, if you go through all this, it's exactly the same problem no matter what you're looking at, as long as all of your loads are in the same plane. Right? Yeah?
So the second is higher for VR over AW times L?
Yes.
Higher than 1 and 2. What's the meaning?
So what's happening there is, if you look at this, because it's a transverse weld, we showed some graphs, I think, in class, where if we had kind of stress strain curves for different welds, we had something that looked like this, where this was at 90 degrees and this was at 0 degrees. Does everyone remember that? So if we look at this weld, it's going to fail on a curve like this. And if we trace this down, at the point where this weld fails, that's where we say we've reached the design point of our structure. We're designing so that this never happens. So we never exceed the yield strength of our material. Now, there might be, depending on what your experience is in design, you might have come across situations where you start to design into the plastic region. That's something totally different. We're not going to worry about that. So when we exceed our yield strength of our material, our ultimate tensile strength of our material, that's where we're calling the failure point, right? Now, when our weld is at this failure point, the rest of our welds, we're going to assume we're all acting at the same, as kind of a unit with this weld. So the strain in our welds, we're going to say has to be all the same. Now there's a little bit of an approximation here, but you can imagine that this is a fairly rigid plate. You can't have completely different strain here as you do over here, right? It has to deform as kind of one piece. So we're assuming that this is a rigid structure. So if the strain in our welds has to be the same across all of them, and the point where this fails is at a lower strain, this is the maximum strength right here that we're going to develop in our other welds before this one fails. So despite the fact that all of our welds are the same length, because this one is going to act more rigid, this actually can handle more stress at the point it fails than this can handle at the point where this weld fails. Does that?
So are those 2 points, like those 2 points represented by that?
So the difference between this point and this point is represented by this first factor here, where this is 1.5 and this is 1. That's because this is roughly 1.5 times this. Now that 0.85 is considering the fact that this limit here is roughly, if you call this 1, then this is roughly 0.85. This is done from experimental work, but it's considering the fact that if this is 1, this is 1.5, and this is 0.85. Can you see where those numbers now come from? So this fails at stress of 1.5. This would fail at a stress of 1, but because we don't get all the way to its failure, we consider to only have a strength of 0.85. Does everyone see that? It gets a little bit more complicated now if you start to deal with welds that aren't at 0 and 90 degrees, where this is still true, but it's a little bit more complicated to draw it out and see where those factors come into play. Because if you have a weld that's somewhere in between, something like 60 degrees, then this is no longer 1 or 1.5, it's somewhere between. We still assume that this, there's some knockdown, but then we have to use the more complicated form of this formula. But it's all based on people doing tests, getting these results, and coming up with what is probably not a perfect representation of the experiments, but it's a way of getting close to an approximation. Because when you're publishing something in a code, it's not always important to be accurate within the 7th decimal place. It has to be a formula, though, that people can actually use. So this is a nice simple representation where you plug in numbers, you get nice round numbers to work with, and it's easy to implement. Does anyone have any other questions before we move on to our last example?
Excuse me?
Yeah.
So I can't understand the meaning of the VR over AW times AW times 0. So what's the meaning of?
Right. So actually, I think I missed an L here. Let me see if that's right. I think so. Maybe not. No. Okay, so VR over AW has, this is the strength that we're calling the strength per unit area that our weld can handle. So this has newtons, this is, this is newtons per millimeter, this is millimeter, so this whole thing has newtons per millimeter. That is the load capacity of our weld. So for each unit length of thickness, for each unit length of weld, we can have some amount of force that our weld can transmit. If we want to compare this to an actual load, we have to convert this to a force. So if this whole package here describes a certain strength or a certain load capacity per length, per thickness of throat, in order to get that to an actual load, we have to multiply by a length and a thickness of throat. Does that make sense? So that's all we're doing here. We multiply by the length here because it's easier to deal with this for each weld, because in this case, all of our welds were the same length, so we could have pulled the length out. But in general, that's not always going to be the case. So you want to deal with this VR over AW over L as a sum. So it's easier if you multiply by all the lengths in your table, and then you just take this package of, I'm not sure if you guys are following what I mean when I say it's a unit. This is basically just a way of capturing the capacity of your weld to handle load, right? Yeah?
A question about the fracture. When the transverse weld breaks, the other one breaks too because it suddenly supports all the load, right? Or is there another reason?
It's a little bit more complicated than that. What we're saying is this is the point where we consider our structure to have failed. What happens beyond this point becomes a question of how this fails, whether it fails plastically, whether it fails by fracture and just disappears. We don't worry about that. If you were to say at this point the whole weld instantaneously fractures through, then we would consider our structure to be failed because all the load would be transferred to this weld, and we're assuming that it's now not going to be able to support that load. But we're not going into those details. All we're saying here is when any part of the weld has reached the strain at which it would fracture, we're going to consider the whole structure to have failed. That's our failure point. We're going to design so we never reach that point. And I think that kind of comes into the concept of limit states design. I'm not a civil engineer, so I'm not going to try to explain what that is to you guys. But it's essentially saying we never want to reach a point where any of our weld has exceeded the strain at which it fails.
So you mean that's a strain is the thing you're really
Looking at it like this, we also don't want to ever reach a point where the stress in our structure has failed, right? When we talked about this. If you look at it where you've got a lot of different welds at different orientations, the strain is what has to be the same in those welds if we assume this is fairly rigid. Yeah? So I'm going through this slowly because I want to try to make sure you guys all have a good grasp of this. We're not going to have a ton of time for our last problem, so we're going to probably not be able to get all the way through it. Okay, so this is a problem we talked about at the very end of class, asymmetric loading. So in practice, this is, I think, the most complicated case that we're going to have you guys look at in this class. Each year, I think the complexity gets a little bit higher. You guys benefit from all the nice examples from the year before you, so we have to make a little bit more, just raise the bar a little bit so everyone coming in the next year sees that we expect something more, and then we can ask them even harder questions. So this is the first time that you'll see this as the examples if you look at the notes from today's class, which I think are going to be uploaded or will be uploaded sometime before next lecture. And this is a situation where on first glance, it might look like we've got the same sort of situation as we had before. We got slightly different lengths for our welds. We got a weld here. The only difference is instead of pulling here, we're putting a vertical load. Now, because we're a little bit short on time, I'm going to try to talk in detail about why this makes the problem different. And we're going to get to the point where it's the same as the other problems. We've already seen that. Hopefully, once we get to the point where we're filling in the columns of that table, we're good there. So if we had a load that was just applied through the center of this, sorry, we'll say this is the center of gravity of our, I'll draw it properly. This is the center of gravity of our weld system. Does everyone see how that would be the center of gravity? We're going to calculate exactly what this length is and what this length is here in a minute. But if we calculate the center of gravity of our welds, if we were to pull through that center of gravity, this problem would be exactly the same as we were dealing with before. So what we're going to try to do is convert this problem to a problem where we're looking at loads through the center of gravity. And what that means is we have to figure out what the equivalent loads are for this if they were through the center of gravity. This is something I think was done a little bit in Civi 270 if anyone's taken any more mechanics courses. Now there's a few mechies in here who probably took more advanced mechanics courses. But that's what we're doing, is we're converting this load to an equivalent load through the center of gravity. Now, this load is going to have 3 components to its equivalent load. It's going to have, so we'll draw our free body diagram here. It's going to have what ends up being a shear load, and then it's going to have bending components. So the bending components are going to be related to the fact that this is acting at an angle to our center of gravity. So if we look at, let me make sure we got this well. This creates some moment, right, relative to this point. And that moment, this is a diagram that was already drawn before, is going to be resisted by forces acting through the welds. In concept, this is all we're going to be doing. Does everyone kind of understand why are you guys with me up to this point? Yeah? So, we end up with an equivalent. The direction's not going to be as critical here, so I'm going to just draw them all in the same direction to make sure it makes sense. An equivalent, we'll call this, what is in my eraser? FH, FV, FS. These equations were given in today's class. If you have a load for a situation where it's a bending acting at some distance from the center of gravity, you're always going to have these 3 components. You're going to have some horizontal force that develops in your welds, you're going to have some vertical force that develops in your welds, and you're going to have some shear force because of the load that's in line with them. The equations we were given for this FH and FV were very similar. I think we were given one was, just make sure, I'm going to make sure I give you guys exactly the right formula here. Just to make sure my notation is exactly the same as your class notes. So, right, so we have a torque, we have a length, and we have J. So this should look familiar to, if you think all the way back to, no, I'm seeing some shakes head that this doesn't look familiar. That's okay. What we're basically looking at here is if we have a moment of inertia which describes our weld, then we have a moment that we're distributing over that area and a length, we can end up with what ends up being here is our required resistance per unit length. So this FH is equivalent to our VR, right? FH is our resistance per unit length of weld. Probably at some point, you guys had if you have a cylinder, right? It's not a very good cylinder, and you have some torque applied to the cylinder, and if this was a very thin ring, you would calculate based on the section property of the cylinder how much torsional stress you had around the cylinder, right? Oh, that's fine. And the formula used to calculate that would look exactly the same as what we're doing here. So what we end up doing is calculating a radius, the CYR, for our cylinder, the torque we're transmitting, And this J is calculated using the properties of our section. Because it's not a circle, the formula for J is not as simple as if it was a cylinder, but we're given those formulas in the class notes, and you'll be given them on the exam. And then functionally doing the exact same thing you did here. Does that make a little bit more sense, maybe? Getting closer?
So would VR equal FR instead of FH?
In this case, what we're going to do is we're not going to worry about a VR. We're going to end up with an F resultant. And that's we're going to substitute instead of VR, because VR is just if there's a shear. Here we're going to have some combination of loading, and we're just going to call it FR. But you're plugging in this into your equation in the place of VR. Those equations we had from the Canadian codes, they're looking at a much narrower situation, but this is general. This works in all kinds of loading, all kinds of situations. And this FR is what happens if you take this load here as a force and this here as a force, and if you add them end to end, that's going to be your FR. So you're looking at, okay, this is horizontal, this is vertical. You end up with FR is the square root of the squares of those components, and that's your resultant force. Now, once you get this force, we talked today a little bit in class, because in this component, we see we've got a force going this way, and this component, the force is going this way. The angle of this force is not necessarily something that's easy to calculate. That's why we said when you start to look at how this load is acting with respect to the angles of these welds, it's a much more complicated mess. So the American codes, or the handbook that we were going off of, they don't even worry about the MW and the sine 1/2. When they get to this sort of situation, they say, okay, we're not going to give ourselves extra credit for having a transverse weld. We won't go up to 1.5. We're also going to not knock down that 0.85. Now, in theory, more conservative would be to say we won't go up to 1.5, and we'll knock everything down to 0.85 to make sure we're always going to be safe. Why they don't do that, I don't know. I'm not a master of the American codes. They don't actually worry about that, some of that stuff in their structural codes the same way the Canadian codes developed. These are all still a little bit of guidelines, and there's some conservatism worked in, so the different codes have different ways of working in their safety factors and their kind of buffer. What's important to remember is the way we taught in class when we're dealing with the MW and the sine thetas, if you have a case where all of your loads are in line and you're asked to calculate it, use those formulas, calculate the angles, consider that, because that's what we taught for the codes. If you have a situation where we're dealing with asymmetric loading, it's perfectly reasonable to say, okay, we're going to assume that we don't give ourselves extra credit for transverse loading, and as long as you say it, we assume we're not going to worry about MW. We're going to assume it's 1. Might not be perfect, might be more conservative to say 0.85. We're going to assume it's 1. Does that make sense? And that's because we can't really calculate easy angles. You could start to say, okay, well, we know this force is going to be horizontal here, and the load's vertical, so this one's going to have, one angle, this is going to have a different angle. You could go through all that mess. This is the first time we've introduced asymmetric loading. That's not going to be something we worry about in this case. So, one thing I want to mention here, that we talked about, we have a CYR and a CXR. So, if we have a vertical force, hopefully you guys all can agree that we're worried about a horizontal length when we're calculating moments. If we have a horizontal force, we're worrying about a vertical length. We're good at that point. Now, what length would we use if we want to be most conservative? The way that this is handled in this sort of situation from the handbook and the codes is they look at whatever point of the weld is furthest from the center of gravity, kind of the worst case scenario. So in this case, our furthest in our horizontal length and our farthest in our vertical length, we would have to calculate where this point of the center of gravity is. Those equations are given. Because we're running out of time a little bit, I'm going to help you guys out here and say that this ends up being, let me just make sure I double check the number. I think it's 93.75 though. So this here, from this edge to the center of gravity, is 93.75 millimeters. That's going to be more than half of 125. This vertical position of our center of gravity, this is 250. Hopefully you guys all can agree. This is getting a bit messy here, but this is going to be 125 millimeters because our weld is symmetric vertically. So if this is closer to this edge, this corner is going to be our furthest point. So the distances we're worried about in this CYR and CXR is going to be the distance from here to this point. CYR or CXR is going to be this 93.75, and CXR is going to be this 125. Does everyone see that? So the CYR is our vertical distance from our center of gravity to our furthest point, and our CXR is our horizontal distance from our center of gravity to our furthest point. Now, another thing to note here, in this case, the point that's furthest vertically and horizontally is the same point. But you could imagine, depending on how crazy this weld looks, there might be a point that's furthest horizontally and a different point that's furthest vertically. So if you want to take the conservative approach, which is what the codes in this set of rules for solving this problem takes, you would have to choose those two different points. But it's just the vertical length to the furthest point vertically and the horizontal length to the furthest point horizontally. Once you have those lengths, really we're just back to the simplest situation. Yes, there is a bit of a complicated formula for calculating this J, but it's completely given for this geometry. You'll be able to match it up exactly. In this case, it's a C geometry. It's going to give you a formula for J, where all you have to do is plug in this length here, this length here. You get your number. You have your CXR, your CYR. T is torque, or moment. But it's called T because it's standing for torque. Our moment here, we have a force, we have a distance, our center of gravity. Because our force is totally vertical, it's a very easy calculation of our moment. It's going to be 80 kilonewtons times 250 millimeters. At that point, we've done all of the hard work of this problem. We substitute in, we solve our FH, our FV. We still have to solve for this FS, but that is exactly the same as what we did for the last situation. That is assuming this 80 kilonewtons passes through the center of gravity. That's basically the whole previous problem gets wrapped up into that FS part, but we're not going to worry about corrections for the angle in that case.
So we could just say FS is 80 kilonewtons?
It's not going to be 80 kilonewtons,
Okay.
because in our case, we're given a formula for FS, which is going to be, I want to make sure I use this notation right, but I think it's V over AW. So we still actually have to calculate an effective let me think about this for a second. We have to calculate what ends up being the effective length for our weld to get that V over AW. Because it ends up being our formula again, where I'm going to write just as an equal here, but actually that's going to make things more complicated. This AW, let me double check this. I think that actually might be a point where these notes are going to become, there might be need to be a correct.
Total length of the weld.
Is it total length of weld? Okay, that makes more sense. Should be, we'll say some L, or I don't know what it says in the notes, something like that. Is it just capital L? Make it nice and easy. Yeah. So that should be the formula we worry about then. I don't know if that's totally consistent with all the different sources. The formulas will be given in your formula sheet for this situation. So this ends up being a similar problem to the first problem. If you ignore all of the off-axis, you could solve the problem of this 80 kilonewtons passing through here, right? And it ends up being the same situation where you're looking for You solve for this FS. If you have that FS, you could solve for your weld size, but before we solve for a weld size based on the FS, we have to first consider other load situations. This ends up being a little bit, so I think part of the confusion here last time, because of the way we were doing our problem where all of the welds were in a table, we multiply by L in our table. This would be more analogous to if we took the sum of the L and actually instead multiplied it by that V over L and compared the VR. We had a table up here where we had VR over AW, and we then multiplied by VR AW over L. That's just a mess now. Right? We had this column here. If you want to use this approach, instead of having that extra column, it's easier to take your load, divide by your total L, and then compare this VR over AW to your V over L. So if you want to do an approach that's going to work for asymmetric loads and symmetric loads, then rather than having this extra column, it might be easier just to always use this formula where you take your vertical load, divide by your total length, and you go right to your VR over AW. The one thing that I have to think about this for a second more, so I'll correct it if it's wrong, but I believe the problem with this approach, if you were to try to do a totally general approach, is we're kind of assuming that each unit length of weld is the same. So if you wanted to have fillets that were different sizes up here, down here, this is not going to let you have that, where the other approach could. So it's not that one is better, it's for different situations. If you have a situation where you have purely symmetric loads, and you may want to be able to consider fillets of different sizes, using the first approach, and it just changes at the very last step, allows you to consider that. But if you want to deal with asymmetric loads, we're not going to add an extra layer of complexity, then worry about different size fillets. So you can worry about taking the sum of the length, dividing by that, and getting your FS. Does that clear things up a little bit? The notes for today's class have all the numbers for this example. I know it's a little bit more complex than some of the other stuff, but if you guys sit down and walk through this a couple times on your own, I think hopefully you're gonna start to see that this is really, once you get the procedure for doing these problems, there's nothing crazy to them. All the hard work is actually trigonometry, geometry, nothing to do with welding and stuff that you guys have encountered in a ton of other classes before this point. It's just learning how to apply the formulas to get that number so you can do what ends up being the easy part then, which is all the weld calculations we learned for the last two classes. Awesome. I think I've already taken you guys 10 minutes over, so we'll call it there.